I hope everyone's doing well. I'm Tommy Wen Chin. I go to San Jose State. I did my summer research through Calbridge, funded by the NSF, and it was a privilege working with Dr. Mu-Chun Chen of UC Irvine on a theoretical neutrino physics project. Today, we're going to ponder about why do we exist. If you take a look at the objects around you, chances are they're made of matter. I'm made of matter, and you are too. San Jose State is made of matter. San Jose is made of matter. The Earth is made of matter. Our sun is made of matter. So are all the other stars. Our Milky Way galaxy is made of matter. So are the other galaxies. That is to say that our entire observable universe is primarily made of matter. In other words, they're made of protons, neutrons, and electrons. Protons and neutrons are made of smaller particles, quarks. Electrons are part of a larger family of leptons. Like anything, matter has its equal and opposite counterpart, antimatter. They're in every way the same, only with opposite charge. Kind of like how x squared equals 4 has two solutions, plus and minus 2. Take, for example, the electron and its counterpart, the positron. For illustrative purposes, we'll switch it to red. When the two come in contact, they'll annihilate each other, producing pure energy. That's what the famous Einstein E equals mc squared equation describes. At the beginning of time, equal proportions of matter and antimatter were created. Since they're in every way the same, there's no reason to favor one over the other. Just like how x equals 2 is no better than minus 2. Now, 13.8 billion years later, you would expect that they'll all eventually annihilate each other, leaving us with an empty universe filled with pure energy. However, I still exist, and you're still here too. Somehow, we're left with more matter than antimatter. Somehow, there's this matter-antimatter asymmetry. And our question is, what happened? What mechanism could lead to such an asymmetry? Physicists believe that neutrinos might hold the answer. Unlike myself, unlike electrons, we maintain the same identity as we travel through space. Neutrinos, on the other hand, consist of three flavors: the electron neutrino, the muon neutrino, and the tau neutrino. They alternate between their identities as they travel through space. We call this neutrino oscillations, which was the subject of the 2015 Physics Nobel Prize. Building off theoretical models by Denton, Park, and Zhang, we plot on the x-axis the distance a group of neutrinos that are traveling through vacuum. On the y-axis, we plot the fraction that are electron, muon, and tau flavors. We started off with 100% mu neutrinos and 0 the others. And depending on where we make our measurements, we'll get different fractions. For example, 80% mu, 20% tau, or 85% tau, 10% mu, and 5% E. If we continue allowing our neutrinos to travel, they'll continue oscillating as promised. What you'll now notice is that the electron neutrinos are starting to shift upwards, whereas the other two comes down. And that's because they all have to add up to 100%. And now the electron neutrinos are coming down. And so they don't only oscillate at the small scale, but also the large scale. Neutrinos are the most abundant particles in the universe. 1 trillion pass through our bodies every second. They can be created as supernova explosions, Our sun currently generates neutrinos, so as our Earth and its atmosphere. We can also create them at particle accelerators. This one in particular is at Fermilab. And we would then send them off to South Dakota for measurements. How far away we send them off for measurements depends on the fraction that we're interested in. Almost all measurements are done underground, isolated from the noise generated by civilization and cosmic rays. Because of that, it is crucial that we model neutrinos traveling through matter as opposed to vacuum. And that is exactly what we did this summer. Among the 3 leptons, electrons are the majority in matter. And so as our neutrinos travel through matter, only the electron neutrinos are affected. The tau and the mu neutrinos zip past through. In our model, we incorporate the parameter A that measures the electron density. In other words, the number of electrons in a given space in matter. And as we increase the electron density, you'll start to notice that the electron neutrino, the green, goes down and down and down. They're all being deflected. In the sun, neutrinos are being created at its core. And as they rise to the surface, they encounter layers of electrons with varying density. Highest density and closest to the core, lowest at the surface. Using solar models by Bacall, Serenelli, and Basu, which was the subject of the 2002 Physics Nobel Prize, we incorporate in our model the electron density of the sun in dark orange. We also divide by the maximum value so that 1 corresponds to the maximum density. We also divide our distance by the sun radius so that 1 corresponds to the surface of the sun. And so again, we start with 100% mu and 0 the others. And while the electron density dark orange is high, you see that the green, the electron neutrino, is low. And as the electron density dark orange comes down, we'll start to see the green, the electron neutrino, come up again. And as the electron density, the dark orange, approaches 0, we'll get back our vacuum oscillations. Now, this is what we're here for. In our model, we have a parameter delta, which measures the charge parity violation. Charge violation is when physics treats matter and antimatter differently. Parity violation is when physics treats our objects and their mirror image differently. Charge parity violation is when we switch our mirror image to antimatter, and if physics treats the two differently, then there is a violation. This difference in physics treatment is a crucial ingredient in explaining the matter-antimatter asymmetry. And so in our model, as we increase the charge parity violation, the delta value, we start to see the green and the blue, the E and the tau neutrinos, shift to the left. When the experiment produced their results, we can then compare them to the plots that we generated with our model and see which one matches the best, telling us the value of delta and the amount of charge parity violation. And when that happens, we might not only address the matter-antimatter asymmetry, we might even answer our bigger question of why do we exist? Thank you.